All right, so we have our carnival swing ride. At this moment in time, at this speed, our rider here is at 60 degrees above the vertical, right? Specifically, you could describe this as 60 degrees east of south, if you like, or 30 degrees south of east, also, same. The length of the chain that connects this rider to the center pole that holds them into this ride is 15.0 meters. We also have the mass of the rider, and that person's mass is 179 kilograms. 179 kilograms. Our question is to find the tension in the cable that's attached to the person that's in the chair. So here's the chair, there's the cable. It's 15.0 meters in length. We're trying to find the tension in the cable, so I'll write that as T. Trying to find that. Specifically the magnitude, we know its direction. And then also the speed of the chair. Trying to find speed. These are the two things. Okay. We need to make an assessment. What are the tools that we're going to have to use to solve this problem? How are we going to find out the tension? How are we going to find out the speed? We have an object that's traveling in a path that is circular, which we would call circular motion, specifically uniform circular motion. I don't have any quantities about initial or final velocity. I do have a mass, and I do have tension, so my mind is also going to some forces that are acting here. So I'm immediately probably going to throw out kinematics. This doesn't seem like kinematics will help me understand the answer here, or figure out the tension or the speed. Forces, yeah, forces might come in here, especially because I'm looking for tension, all right? And then definitely this is predominantly a horizontal circular motion sort of problem. So I'm thinking of centripetal forces, centripetal acceleration, and relating them to each other, relating that to sum of forces, to Newton's second law. All right, so where to begin? All right, let's see. What might be helpful is starting with a free body diagram, I think, here. I think a free body diagram, because I need to get a sense of what is the centripetal force here. It's not the tension. It's only a component of the tension. The tension is doing two things here. It's both supporting the weight of the person, and it's contributing to the circular motion of the person. So I'm going to draw a free body diagram to try to make that clear. I'll draw that over here. So if I draw a free body diagram of our rider here that has a mass of 179 kilograms. They have some weight pointing down. Okay, there's their weight vector because they have a mass. And then there also is the force of tension that's acting on that rider. Force of tension that's acting on that rider. There's our force of tension. All right, I need to get a sense of the angle here that's acting, though, because I know the 60 degrees is right here. So a little bit of geometry. That's part of what makes this a little tricky. If that angle right there is 60 degrees, to relate it back up to this problem, I know that if I make a plane right here, that this angle right inside there, that should be 30 degrees then. Do we see why that is? Do I need to stop in? Okay, so I can visualize abstractly. Here's like a right triangle. I can see there's a right triangle. If that's 60, that must be 30 right there. So I'll be able to find it's 30 degrees north of west is the force of tension that's acting on this person. All right, great. All right, so now that I have a free body diagram, let's look at forces. Hopefully I can unite, and I should be able to, circular motion and centripetal forces to the forces that are acting on this object. I have two dimensions of forces that are acting here. I have both the centripetal dimension, which we'll analyze, and I also have looks like the vertical here. So we'll also look at forces that are acting in the y dimension. So we'll analyze the two dimensions of forces that are acting on this rider. The centripetal forces, there's only one, and that is the x component or the centripetal component of the tension. I'm going to write that as T sub c. And I'll draw that vector in to try to make it clear which vector that is. That would be this projection of the tension. And then there's the other projection of the tension that's pointing up, that's supporting the weight. I'll call this T sub y. And here's T sub c. So this is what I mean when I say that that tension force is accomplishing two tasks. It is both supporting the weight, it's overcoming the weight, right? So really, I should have drawn this tension in y just as long as the weight. But it's also providing the force that keeps the object in the circle. There has to be a continual force that keeps our rider in a circular motion, and that would be the centripetal component, or this looks like an X projection, right? Looks like an X projection of the tension. And that is the only centripetal force I have. So the centripetal component of the tension must be what's supplying the centripetal force. I know that the magnitude of that force equals, based upon my equations, I go back to my fundamental critical equations, mass times the speed of the object squared divided by its radius. Okay. All right. I still don't have, remember, I'm trying to find speed and not centripetal tension or that component, but the whole tension. So I'm not quite there yet. I still have a little bit of a ways to go, it seems. There's not much I can do. I do have the mass. I don't have the speed. I actually know I can find the radius through a little bit of geometry again. If I go up to my picture up here, if I look at this part of the triangle that's created here, right? This is the component that is the radius. I know that if this is the hypotenuse, the circle that this object is actually going around has this radius, not this radius. That's just the length of the cable. The radius is actually this horizontal projection. That's the actual radius. I have the hypotenuse. I have this angle here. I can find what that radius is. I can quickly do that. I know that if I take this would be the sine. So if I take sine of 60 degrees, 60.0 degrees, sine of that angle, the opposite is the radius, divided by my 15.0 meters. I can find that the radius is equal to 15 sine 60 degrees. 15.0 sine of 60.0 degrees. That's my radius. All right. Good. That was a little tricky because it's not immediately apparent that I need to do that, but that is the actual radius of the circle that this object is traveling around. It's not 15. If it was 15, then this part of this rider would be all the way up here. He'd be over here. Since he's dipping down, then it's actually less than 15.0 meters. Okay, we have the radius, great. We have the mass, great. I don't know the centripetal component of the tension, and I don't know the speed. So I'm going to have to start looking at forces in y. Do a little bit more analysis. All right, forces in y. Look at my free body diagram. I have weight, right? That's one of them, and I have tension in y. Tension in y and weight. Those are the two forces that are acting in the y dimension. What is the acceleration in the y dimension? Is my rider accelerating up or down as they go around in the circle? No. They're staying in the same circle, right? The circle's not changing. It's the same singular circle. They're not accelerating up or down. So I know that mass times my acceleration of 0 in the y dimension is the net force in the y dimension must be equal to 0. And I'll write that out as the acceleration in y is 0. Not moving up or down at all. It's just moving in a circle, uniform motion. So I can immediately tell that these two forces must be equal to each other in magnitude. Must be equal to each other in magnitude. That's great. That's a lot of good news because this weight I know I can calculate because I have the mass and I know the gravitational field, so I'll be able to find the tension in y. I know if I have tension in y, remember if I go back here, if I find tension in y, now I have one side of this vector triangle. I should be able to find this other side of the vector triangle because I'd have the magnitude of one side and an angle within the triangle. Okay. All right, so I can find tension in y. That would be my 179. See, 179 times gravity. Okay, 179 kilograms times my gravitational field of 9.80 newtons per kilogram. Okay. I'll put that in my calculator real quick. Let's see, 179 times 9.80. Okay. To three significant figures, I have 1,750 newtons. 1,750 newtons. Okay. That's the tension in y. That is the force that the tension exerts on the person to support their weight. right? Remember, the tension's accomplishing two tasks. It's both supporting the weight and it's contributing to centripetal motion. All right. Now that I have tension in y, now that I have one side of the triangle of this vector triangle, and I'll make that bigger for us. So I'll look at our tension triangle here, tension in y. Then I have my centripetal here. There's my centripetal tension. Here's my resultant tension. Remember, I have this side, and I have one of these two angles. If I look back at this picture, I could say that's 30 degrees, and that's 60 degrees. So this is 60, this is 30. I just need to relate them to this tension in y to our centripetal force, the tension in C. Are we still following? Okay, good. This is a hard problem. All right, so I can relate this 1750 to tension in C, and then I can see if I can find tension C, then I can find what the speed must be. Because remember, I found radius already. I know the mass. I would find tension in C, so I can find the speed. Remember, we're trying to find the speed and the tension in the cable. Okay. To relate 60 degrees, tension in y, and centripetal tension, I need to use, let's see, this is the opposite side. That's the adjacent side. So I'm going to have to use tangent. So tangent of 60 degrees equals my opposite, which is tension in C, the magnitude of that force, divided by tension in y. All right, I know tension in y, that's 1750. So I can rearrange this equation and find that 1750 newtons times the tangent of 60 degrees equals my centripetal tension, or the component of the tension force that's contributing to centripetal motion. Okay. I can calculate that real quickly. 1750 times the tangent of 60 degrees. All right, 3031.1. I have three significant figures here. So 3030 looks like. 3030 newtons of force. Okay, this is a two piece of information I have so far. All right, remember this is the centripetal tension component, so I can relate it back up here. Okay, so I'll go back up here and say that I know this whole mass times my acceleration, my speed squared over r, is equal to 3030 newtons, or 3030 newtons. I know the radius, I know the speed, or rather, I know the radius, I know the mass. I just need to rearrange this equation to find the speed. I know if I rearrange that equation, I can rearrange it to looks like whatever my tension in C is that I just found, which is the 3030, times r divided by m, and then the square root of that quantity. Do we see how I got there? R is going to move over to the other side, divide by m, and then take the square root. Now I'll be able to find what the speed of this rider must be. So square root of my 3030 times my radius that I found, which is 15.0 times the sine of 60 degrees. Okay. All of that divided by the mass. Okay. Divided by the mass of 179. Okay. My speed comes out to 14.8 meters per second. All right. That answers one question. So that must be the speed. Okay. Speed must be 14.8 meters per second. My last question is, what's the tension in the chain that's connecting this rider? What's the tension in this chain that's connecting the rider to this ride? That's, again, just another question of trigonometry here, because I already have this triangle. So now I just need to find this t here. I could use the Pythagorean theorem if I like, because here's my tension in y, one leg of the triangle. Here's my tension in my centripetal tension, or my x component of the tension. So I could square those and then take the square root, and I would have found the tension. So I'll write that out. I know that the magnitude of the tension will be equal to the centripetal tension component squared plus the tension in y squared, the square root of that quantity. Okay, so I'll find that the tension is, let's see, 3030 squared plus 1750 squared. quantity square root. 3,500. 35. So to keep 3 significant figures, go like that. There is the tension in the cable that's supporting the rider. So they're traveling at a speed of 14.8 meters per second around this ride. And the tension in the cable is 3,500 newtons. Let's see what important physics we can glean from this. Because relating to if our speed gets larger. So if the speed here gets larger, what happens to the centripetal tension? Also must get larger, right? They go up together. Right? If the mass gets larger, then the speed goes down. That makes sense because the mass depends on, the mass relates to the weight, right? So the more that the weight pulls down on the object, then the smaller the circle will be, right? Okay. That's that problem.